Welcome to Einstein's theory of relativity, a revolutionary framework that transformed our understanding of the universe. In 1905, Einstein published his theory of special relativity, followed by general relativity in 1915. Special relativity introduced two revolutionary principles. The laws of physics are the same for all observers, and the speed of light is constant in all reference frames. This leads to the profound conclusion that time and space are not absolute but relative, depending on an observer's motion. One of the most fascinating consequences is time dilation. Time passes more slowly for objects in motion. This is illustrated by the famous twin paradox, where a twin traveling at high speed ages more slowly than their earthbound sibling. General relativity expanded these ideas to include gravity, which Einstein described not as a force but as a curvature of spacetime caused by mass and energy. In Einstein's view, massive objects like planets and stars create a depression in the fabric of spacetime, causing other objects to follow curved paths around them, what we experience as gravity. Einstein's theories of relativity revolutionized physics, replacing Newton's understanding of gravity and transforming our conception of space and time as fundamental, separate entities into a unified four-dimensional spacetime. These theories continue to be tested and validated today, forming the basis for our understanding of black holes, gravitational waves, and the evolution of the universe itself. In the next section, we'll delve deeper into special relativity and explore its foundational principles. In 1905, Albert Einstein introduced his revolutionary theory of special relativity. This groundbreaking theory, published when Einstein was just 26 years old, fundamentally changed our understanding of space and time. Special relativity focuses on the relationship between space and time for observers in inertial frames of reference. An inertial frame is simply a frame of reference that moves at constant velocity with no acceleration. Special relativity is based on two fundamental postulates, which led to revolutionary consequences. The first postulate states that the laws of physics are identical for all observers in inertial reference frames. This means there's no way to determine which inertial frame is truly at rest. Whether you're standing still or moving at constant velocity, the laws of physics behave the same way. The second postulate is even more revolutionary. It states that the speed of light in a vacuum is constant for all observers, regardless of the motion of the light source or the observer. This means that light always travels at approximately 300 million meters per second, no matter how fast you're moving relative to the light source. To understand the implications of these postulates, let's consider a thought experiment using a light clock. In a stationary reference frame, light bounces directly up and down between two mirrors. But when the clock moves, the light follows a diagonal path. Since the speed of light must remain constant, time itself must slow down for the moving clock. Another mind-bending consequence of special relativity is length contraction. As an object moves faster, its length in the direction of motion appears to contract according to this formula. This means that a moving object will appear shorter to a stationary observer. Special relativity leads to several counterintuitive consequences that fundamentally alter our understanding of reality. These include time dilation, where moving clocks run slower than stationary ones; length contraction, where objects appear shorter in the direction of motion; the relativity of simultaneity, which means events that appear simultaneous to one observer may occur at different times for another; and perhaps most famously, the equivalence of mass and energy, expressed in Einstein's equation E equals mc squared. Einstein's special theory of relativity fundamentally changed our understanding of space and time, setting the stage for even more revolutionary ideas to come. Special relativity gave us the most famous equation in physics, E equals mc squared. This elegant and simple equation, developed by Albert Einstein in 1905, demonstrates the equivalence of mass and energy. Mass and energy are fundamentally interchangeable forms of the same physical entity. This means that mass can be converted into energy, and energy can be converted into mass. In this equation, E represents energy measured in joules, M represents mass in kilograms, and c is the speed of light, approximately 300 million meters per second. Because the speed of light squared is an enormously large number, even a tiny amount of mass can be converted into a tremendous amount of energy. To put this in perspective, 1 kilogram of matter converted entirely to energy would produce energy equivalent to 21 megatons of TNT, or the annual electricity consumption of about 2.7 million American homes. Nuclear fission demonstrates this principle in action. When a neutron splits a uranium atom, a small fraction of the mass is converted into energy. Mass energy equivalence is the scientific principle behind nuclear power plants. In these facilities, controlled nuclear fission reactors convert a small amount of nuclear mass into substantial energy. The same principle enables nuclear weapons. The atomic bomb dropped on Hiroshima used less than 1 kilogram of uranium, but produced an explosion equivalent to 15,000 tons of TNT by converting a fraction of its mass to energy. Beyond practical applications, Einstein's equation has profound implications for our understanding of the universe. Since mass and energy are equivalent, energy also curves spacetime just as mass does in general relativity. Einstein's E equals mc squared is much more than a famous formula. It's a profound statement about the fundamental nature of our universe, where mass and energy are simply different manifestations of the same thing. Einstein's theory of general relativity has been confirmed by numerous astronomical observations since it was proposed. One of the earliest pieces of evidence supporting general relativity was the anomalous precession of Mercury's orbit. While Newtonian physics predicted that Mercury's orbit should form a perfect ellipse, astronomers had observed a slight wobble or precession of 43 arcseconds per century that could not be fully explained. Mercury's orbit shows a precession effect where its elliptical path gradually shifts position with each revolution around the Sun. This side-by-side comparison shows Mercury's orbit as predicted by Newtonian physics versus general relativity. Einstein's equations precisely predicted the 43 arcsecond precession that Newtonian physics could not explain. General relativity's effects can be seen across our solar system. These graphs show planetary positions over time, with each planet experiencing different amounts of gravitational influence based on its proximity to the Sun. Another striking confirmation of general relativity is gravitational lensing. According to Einstein, massive objects bend spacetime, which causes light to follow curved paths. This illustration shows how light from a distant star bends as it passes near a massive object like a star or galaxy. The actual position of the star differs from where we observe it due to this bending effect. In some cases, when light from a distant galaxy passes a massive object almost perfectly aligned with our line of sight, it can form a complete circle, known as an Einstein ring. This image shows an Einstein ring formed by light from the distant galaxy PSS J2322 plus 1944. The light is bent and magnified by a closer lensing galaxy, creating this distinctive ring-like structure. Gravitational lensing has important scientific applications. It allows astronomers to observe galaxies that would otherwise be too faint to see directly. It helps measure the distribution of dark matter in the universe, and it provides estimates of the universe's expansion rate. These observational confirmations of general relativity demonstrate the remarkable accuracy of Einstein's theory in describing gravity as the curvature of spacetime. Gravitational waves are remarkable ripples in the fabric of spacetime, one of the most significant predictions of Einstein's theory of general relativity. These waves are produced when massive objects accelerate, creating ripples in spacetime that travel at the speed of light. As gravitational waves pass through space, they stretch and compress it in alternating directions. Gravitational waves can be generated by several cosmic events. The strongest sources include merging black holes, colliding neutron stars, supernovae explosions, and even processes from the early universe. In 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, made history by directly detecting gravitational waves for the first time. This observatory consists of two L-shaped detectors located in Washington and Louisiana. LIGO works using laser interferometry. When a gravitational wave passes through the detector, it slightly changes the lengths of the perpendicular arms, causing the laser beams to fall out of phase. This creates an interference pattern that scientists can measure. The first gravitational wave detection, designated GW150914, captured the merger of two black holes located 1.3 billion light-years away. These black holes had masses of 36 and 29 times our Sun, forming a final black hole of 62 solar masses. The missing 3 solar masses were converted to energy in the form of gravitational waves. Black hole mergers are among the most powerful events in the universe since the Big Bang. During a merger, these systems briefly emit more energy in gravitational waves than all the stars in the observable universe combined. Each detection provides crucial information about the masses, spins, and distances of these extreme objects. The detection of gravitational waves has opened an entirely new window into the universe. Unlike light, gravitational waves can travel through matter unimpeded, allowing us to observe phenomena that are otherwise invisible. They enable multi-messenger astronomy, where cosmic events are studied using both gravitational waves and electromagnetic radiation. This new field helps test general relativity in extreme conditions, understand neutron star composition, and even measure the expansion rate of the universe. Gravitational waves have truly revolutionized our ability to observe the universe's most violent and energetic phenomena, confirming Einstein's remarkable prediction and opening new frontiers in astronomy.